Welcome everybody to the SC4D Subduction Zones in 4 Dimensions International Webinar Series. This is our 3rd international webinar focused on hearing from groups around the world and their recent progress on understanding the fundamental processes underlying hazards in subduction zones. SC4D is an ongoing initiative aimed at planning large-scale experiments to understand fundamental processes in subduction zones focused on large earthquakes, faulting and earthquake cycles, magmatic drivers of eruptions, and landslides, the landscapes and seascapes group. So we will be highlighting these different topics throughout this seminar series. And you can find announcements of future seminars as well as recordings of previous ones at our website, sc4d.org. So I'm going to start by announcing the next webinar, which is on September 25th, and will be given by Dr. Maria Teresa Ramirez Herrera. This one will focus on unearthing geological and historic evidence of large earthquakes and tsunamis on the Mexican subduction zone, results, problems, and future studies. Today's webinar is the first focused on volcanic processes, and I also want to announce that the next volcanic themed webinar in this series will be given by Silvana Hidalgo on October 23rd. So please stay tuned for an announcement of that webinar, and please check our website for details. So today's webinar is jointly given, and I'm pleased to announce our 2 speakers, Mauricio Mora, who is a senior professor at the University of Costa Rica, where he's director of the Central American Geology School, and also the volcanologist working with the National Seismic Network in Costa Rica. So he's a volcanoseismologist. Our second speaker today will be Maarten de Moor, who is a professor with OVISCORI at the Universidad Nacional de Costa Rica. He's also an adjunct professor at the University of New Mexico, and his research focuses on gas emissions and understanding fluid processes in volcanic systems. So they will be jointly giving today's talk, which will focus on phreatic eruptions. And this is a very poorly understood but extremely important aspect of volcanism. So I'm very pleased that they're going to kick off the magmatic drivers eruption portion of this webinar. And I'm very much looking forward to hearing about their recent work on numerous phreatic eruptions in Costa Rica. So I'll just note that during the webinar, please mute yourself and turn your camera off so that we can run this smoothly. We have a lot of people on the call. If you have any questions, please, for the speakers, please type them into the chat window. We'll go through and won't interrupt unless there are technical issues. And then at the end, I'll read through the questions in the chat window and ask the speakers to address them. So we'll hold questions until the end, but please feel free to enter them at any time. So with that, Mauricio and Maarten, thank you so much for joining us. I'll turn it over to you, and if you'd like to go ahead and share your screen and take it away. Thank you.
Okay, good morning, Diana. Thanks for the introduction. I am actually going to be giving the talk. We decided this would make more sense. So let's see. Can everybody hear me okay?
Yes, perfect. And
okay.
You can see.
Okay, great. So yeah, thank you very much for the introduction. I'm very happy to be talking to you today about one of my favorite topics. And actually, in the end, we decided to include a bunch of people, and I'm just representing the important work that is being done by this group, which includes institutions. I'm at OVISCORI at the National University in Costa Rica. We've got La Red Sismológica Nacional, la Comisión Nacional de Emergencias, and we're all sort of in charge of volcanic hazard assessment in Costa Rica. And we also work, I'm also representing some of the work being done with our international colleagues in North America. So thank you everybody for your contributions. The first point I'd like to make is that these small, let's call them phreatomagmatic eruptions, are severely underreported. This plot on the left-hand side here is showing the eruption catalog of Javier Pacheco at OVISCORI. And what we see is that since 2015, there have been 7,135 eruptive events recorded so far. And if we compare that to the Smithsonian Global Volcanism Program, there have been 8 eruptions reported there since 2015. So obviously we're not even reporting or recording the vast majority of these eruptions. And this is also reflected in the fact that our rapid eruption reporting at OVISCORI, we've reported less than 10% of all of those eruptions. So part of the problem is an inconsistency, I think, about what's an important eruption and what's a not important eruption. And obviously that's a very subjective issue and depends on a lot of social factors as well as scientific factors. Part of why we're seeing so many eruptions now is because of like a lot better monitoring network that we have in Costa Rica, which has improved significantly over the last decade or so. At OVISCORI, we now have seismic and infrasound at our volcanoes. We have a large GPS network. We have multi-gas instruments scanning DOAS. We have webcams. We have a Doppler radar. We're using drones as well. So all of these contribute a lot to our understanding of these eruptions. And in Costa Rica, we also have the National Seismic Network, which is basically like a parallel seismic network covering the entire country as well. So yeah, we have a lot of data on these eruptions. And why are they so important? These small phreatic or phreatomagmatic eruptions. Well, there have been a number of recent terrible tragedies, like the recent one at White Island, where 21 people died, and this raises a lot of questions about what we understand about these eruptions and how we can monitor them better. Another example is the Ontake eruption in 2014, which killed 60 people hiking on the volcano. So, as I've already shown, these eruptions are very common and severely underreported. And actually, when we talk about phreatic and phreatomagmatic eruptions, this is a diverse family of eruptions, is how I would put it. They are hazardous. They're more explosive than magmatic eruptions. And their hazards include ballistics, base surges, lahars, ash emissions, and gas and acid emissions, all which affect surrounding areas. These small phreatic and phreatomagmatic eruptions may be precursors to larger magmatic eruptions in some cases, and so it's important that we can distinguish between ones that lead to magmatic eruptions and ones that do not. The processes driving these eruptions are complex, and we don't understand them very well, I would say, but they involve interactions between hydrothermal systems, which are complex in and of themselves, and magmatic systems that are also complex. So this is a fertile area for further study. Today I'll be talking about eruptions in Costa Rica and highlighting some key monitoring observations from Poas, Turrialba, and Rincon de la Vieja. Then I'll make some comparisons with other volcanoes like Ontake, which is now well studied, and some well studied eruptions in New Zealand. And then end with some discussion on the processes and the terminology that we use to describe these eruptions. So this is Poas volcano, and the typical types of eruptions that we've seen at Poas in recent years. On the upper left here, we have an eruption that's occurring through the crater lake, for which Poas is quite famous. On the right-hand side, we see an eruptive column in 2017. So this 2017 eruption sequence was the biggest eruption at POAS since the 1950s. So quite an important event. And after this eruption, at the bottom left, we can see that what happened was there was significant ash emission of mostly magmatic material. At POAS, one of the defining features of this volcano is its hyperacid warm lake, shown on the top right. And this is a very well-studied lake in terms of its geochemistry and composition, temperature, and pH. And what we can see is that there are large variations in sulfate to chloride ratios in the lake, and that these are associated with changes in volcanic activity. But in fact, this lake is actually the surface manifestation of probably a much larger, extensive hydrothermal system. And what this plot on the bottom right is showing is that many of these hydrothermal minerals are saturated or oversaturated in these sublimnic hydrothermal system fluids. And these minerals can seal the vent. And that's what we think is an important process in driving larger explosive eruptions of this volcano. So in terms of gas geochemistry, you can see here from the main 2017 eruption that we saw a huge change in the ratio of SO2 to CO2 right before the eruption. But in the year or year and a half leading up to this eruption, we saw a big decrease in this ratio, which we attribute to precipitation of sulfur-bearing minerals in the system that sealed the vent and primed the system for this much larger 2017 eruption. We also have direct evidence from geodesy, from the GPS network, that there was magma intrusion associated with this eruption in the initial phases. And so immediately we are coming into this discussion about whether magma is driving the system or whether it's hydrothermal sealing that's leading to these bigger eruptions. There's no doubt that magma was involved in this eruption, at least after the initial phases. On the left-hand side, you can see this huge plastically deformed bomb that was erupted. But magma was involved, but was it driving the eruption? And if so, which magma? This plot on the right is showing electron microprobe data from fresh, glassy-looking, juvenile, quote-unquote, clasts. And we can see that there's a huge diversity in the magmatic eruptive products. So which one of these magmas is responsible for the eruption, if it is responsible? It's an open question. And so this is also getting into the PhD work of Montserrat Cascante from OVISCORI, who's now at the University of Oregon, who's looking at class size distributions and class morphologies to better understand the magmatic hydrothermal interactions that were occurring during the various phases of this eruption. But again, I think from a monitoring point of view, it's very important to be able to identify this sealing, this hydrothermal sealing of the system. Something that most observatories monitor is SO2 flux, and we can see that right before this eruption, SO2 flux from the volcano was below detection limit. So when we're not seeing magmatic gases reaching the surface, that can be a very important clue that the system is sealed and potentially leading up to a bigger explosive eruption. So the last important eruptions that we had at POAS were in September last year, and this was a great success from a seismic standpoint because the seismologists were able to quite clearly see that the volcano was entering a more eruptive state. And this is Javier Pacheco's monitoring work. And what we can see is that before the eruption in late September, we saw that there was a period of tremor, followed by an increase in LPs, small eruptions, and then these larger explosive eruptions. And after the eruption, then the LP activity went back to normal. And something that the seismology group has been working on is a very impressive continuous automatic form of monitoring the seismic behavior of the volcano. And again, here, looking at these continuous analysis results, there were significant changes in some of these parameters prior to this phreatic or phreatomagmatic eruption. So this is giving us some confidence that we can forecast some of these eruptions in a better way. So moving on to Turrialba, these photos show some of the typical eruptive activity at Turrialba volcano, and we can immediately see that these are quite different from the eruptions at Poas. These have also been described as phreatic or phreatomagmatic eruptions. This is an overview of the activity looking at the volume of ash emitted as a function of time. And in total, the total amount of ash that's been emitted since 2010 is very small, less than 0.02 cubic kilometers. On the 29th of October in 2014 was a major change in the behavior from a couple of small ash emissions to a large, well, an event opening eruption that that was followed by a significant increase in ash emission. So not much material was erupted, but the impacts have been quite severe for Costa Rica because Turrialba is located directly upwind of the Central Valley, which is the economic heart of the country. So even these small eruptions can be very important and have large impacts on society. As shown here, about 3 million people were impacted by these ash emissions. They caused significant flight disruptions and school closures. All of this is almost irrelevant now compared to what's happening with COVID-19, but at the time, these were significant economic impacts on the country. So again, looking at the seismicity associated with this activity, what we see is quite a diversity of seismicity at Turrialba. There are tens of LP events per day. We have LP, high frequency LP events, according to Javier's terminology here. The eruptive activity has decreased significantly, but in red you can see that we saw a significant number of passive ash emissions in June to August of this year. We see occasional swarms of VTs and some LP plus tremor events, which are also important in terms of understanding the behavior of this volcano. And again, we have this continuous analysis that Mauricio Mora and Javier and others are working on to continuously in real time be assessing the seismic data. So here's an example, April of this year, of an LP event followed by harmonic tremor. And these events can display gliding or lack of gliding. But these LP events are in some cases quite closely associated with these passive ash emissions. So this is telling us about something about fluid movement in the system and how they're potentially generating these eruptions. Another important seismic precursor, especially in some of these larger explosive or eruptive events, such as in 2016, were these tornillo type seismic events, named because they look like a screw. Tornillo Spanish means screw in Spanish. And we can see that the frequencies on the right plot here show significant changes which seem to be related to eruptive activity. And this is the work of Leonardo van der Lat at the University of Costa Rica. So keep a lookout for this work. In terms of the geochemistry, during the initial phases of the eruption, we saw some significant changes in the gas chemistry, particularly these spikes of CO2-rich gas before the eruptive events. And on this bottom plot, basically the disappearance of H2S after 2015, which we interpreted to show the change from more hydrothermal dominated conditions to more magmatic dominated conditions. Now, since those initial phases, the gas ratios have not been very useful in forecasting. Basically, we see a lot of scatter in these data. So, but something that does stand out still is that this H2S just dropped off in a very impressive way after the initial vent opening type eruptions. And just now that the volcanic activity is decreasing, we see that H2S is coming back into the system again. Something that's been quite successful, I think, in terms of monitoring and forecasting is also the geodesy and looking at the deformation. This plot on the bottom is showing these ramps up in the GPS position before some of the more active periods. And interestingly, this the source of this inflation is actually located beneath Irazu volcano, which is 12 kilometers away from Turrialba, which opens many questions about how this plumbing system works and what the connections are between these two volcanoes. There's no doubt, again, that magma is involved in this. We have, as shown, that deformation data. This we can see on this picture up on the top right. This is a bomb that was erupted in 2017, I believe. But this is clearly, was molten at the time of eruption. But if we look at the ashes, actually the component of truly fresh juvenile material is quite low, between a few percent and up to maybe 40%. So just by looking at the ashes, we can see that the dominant component again is hydrothermal. So again, the volume of ash that was actually erupted is hard to constrain with these small eruptions, but it's somewhere between 0.003 and 0.015 cubic kilometers. Some of this volume can be explained just by excavation, explosive excavation of material from the crater, but not all of it. And if we compare these values to the amount of intruded magma from deformation or from the total amount of gas that's emitted, we can see that, or we think that the amount of magma that's been intruded is a lot more than what's been erupted, especially considering that only a minor component of this ash is actually juvenile. So we can't explain all of the deformation or all of the gas with the amount of magma that's been erupted. Definitely not, which raises questions about how much of this deformation is hydrothermal and how much of the gas is in fact potentially remobilized from the hydrothermal system. These are also open questions in these kinds of eruptions. If we look at some of the juvenile component in these ashes, these are images from Alvarado et al. 2016, and we can see some of these juvenile particles have definitely experienced quenching, for example, with these quenching cracks, suggesting that some of this explosivity is associated with fuel coolant interactions directly between the magma and the hydrothermal system. However, again, similar to the situation at POAS, we see that if we look at these juvenile fragments, this is a plot from Dimitri et al. 2019, that there's a huge variety of compositions of the quote-unquote juvenile component. So if we think that magma's driving the eruption, well, which one? You can choose anything you like here, and proving which one is driving the eruption is a very difficult exercise. We also have evidence that this hydrothermal sealing process is important. So in this 29th October vent opening eruption that happened in 2014, we saw that there were a lot of these hydrothermally sealed volcanic breccias that were erupted. And these are very interesting rocks. that Emily Mick at McGill is studying for her master's with John Sticks. And what we can see is that the permeability and porosity of these breccias is very low due to the precipitation of gypsum gypsum and anhydrite that's filling fractures. We have alunite forming as a major hydrothermal mineral, and we also have pyrite. So the precipitation of these sulfur-bearing minerals must be playing some role in the volcanic gases that we see, and also in sealing the system, we think, priming the system for more explosive eruptions. Okay, so moving on to Rincon de la Vieja. This is actually the most active volcano in Costa Rica at the moment. And these photos show the kinds of activity that we see, which are more similar to some of the eruptions that we see at POAS. And this is related to the fact that some of these eruptions are occurring through a hyperacid crater lake as well. So we can see that these are very steam-rich columns, and that the solid material, or that the eruption columns are very water-rich and include lake sediments and rocks. So June of this year was a time of where we saw tens of eruptions per day. And this figure on the left is showing this beautiful banded tremor on the bottom. And some of these tremor events are directly associated with infrasound signals that are attributed to explosive eruptions. And on the right, we can see the relationship between probably an LP event followed by tremor associated with an infrasound signaling an eruption. So far this year, there have been over 1,200 eruptions at Rincon de la Vieja. So these are very common events. The largest one of these occurred on January 30th. And you can see in this webcam image kind of that this is a significant eruption ejecting a large amount of material from the shallow hydrothermal system. The plume reached about 1.5 kilometers in this case. So if we're looking at the seismic signals associated with Rincon de la Vieja, we see again a variety of seismicity from VTs and tornillos to this very distinctive banded tremor. And this eruptive peak shown in blue was associated with this increase in the amplitude of this banded tremor. The continuous analysis conducted by Mauricio Mora and Javier and others also shows significant changes in this tremor and its characteristics with eruptive behavior. If we look at the VTs and the distribution of VTs around the volcano, this is in the top left here, we see that the VTs are seem to be suggesting the intrusion of a dike-like feature in the edifice. So this is interpreted as potentially the intrusion of a dike into the shallow hydrothermal system that's then perturbing the system and driving these eruptions. The GPS data also indicate that there's inflation also consistent with a similar dike. So we're getting a picture here that these phreatic or phreatomagmatic eruptions are ultimately related to the intrusion of magma. If we look at the gases, this is a difficult volcano to monitor with gases, but for a while we had a multi-gas instrument up there, and we saw that the degassing behavior is quite different from what we see at Turrialba or at POAS, where we see on the top left here high CO2 SO2 ratios and high H2S SO2 ratios until the actual eruption, at which case we see big increases. It's basically a pulse of magmatic gas that's being released through the system. So our interpretation of that is that the conduit is essentially sealed or partially sealed in between these eruptions, and then it opens explosively, releasing magmatic gases, and then it seals quite rapidly again. And in terms of the most recent eruptions, Alejandro Rodriguez from OVISCORI did a number of DOAS traverses during the peak of this eruptive period, and we see moderate SO2 fluxes, except for one point here, which is significantly higher, which is probably directly associated with the pulse of magmatic gas released by one of these explosive events. The ashes from Rincon de la Vieja really haven't been studied in great detail. And this is, but what Maria Martinez has shown is that if we look at the ash leachates, we see that the sulfate to calcium ratio in these ashes is very consistent. This is a concentration ratio, but if you convert that to a molar ratio, that's essentially a 1-to-1 calcium to sulfate ratio, suggesting that these components are coming from gypsum or anhydrite. And in fact, we just have some new samples collected by Waldo Taylor just from, within the last couple of weeks. And if we look at these ashes, we can see these distinctive crystals in the ashes that look like gypsum. So explaining potentially these calcium to sulfate ratios. And this is suggesting that, again, we have a hydrothermal seal formed by these sulfate minerals. Like in the other cases, if we look at these ashes, we see that there is a juvenile component. This is Geoffroy Avard's work. And on the right-hand side, we can see some nice, fresh-looking glassy material, again suggesting that there is some magmatic contribution here, but the percentages are minor, less than 20% of this fresh glassy material. So if we summarize some of these observations for the Costa Rican volcanoes, we can see that these quote-unquote phreatic eruptions have evidence for magma involvement in pretty much all cases. So we see deep inflation, we see the patterns of seismic activity, which suggests magma intrusion. We see magmatic gas compositions, particularly emitted during the actual eruptions. And we see a component of fresh glassy material. There's caveats to all of those as being a smoking gun for magma involvement, but taken together, I think it's pretty convincing that there is magma involved. We also see that hydrothermal sealing is a very important process. This leads to accumulation of magmatic volatiles, generation of overpressure, and we think that these hydrothermal seals are composed of elemental sulfur, gypsum and anhydrite, alunite, silica or various polymorphs of silica, and pyrite. This is basically advanced argillic alteration assemblage. And one key message for volcanic monitoring is that the more sealed the volcano, potentially the more dangerous the situation is, and the larger and more explosive the eruptions can be. We also think that interaction with exogenous water is important. Some of these eruptions occur through crater lakes, so that's the most obvious clue that about the role of water. We also see diverse seismic signals, suggesting that there are many types of fluids interacting or moving through the systems, and the role of these fluids must be important. With the juvenile component of the ashes, we can see that there are quench morphologies, indicating that there's some degree of direct magma water interaction going on. And we also see big changes in the gas emissions when these hydrothermal interactions between magmatic gas and meteoric water are taking place. So these are all tools that we can use to try to understand a bit better how these systems work. But what is the dominant process? This is a very difficult question, but somehow it's related to the terminology that we use when describing these eruptions, because phreatic eruptions are supposedly don't have magma involvement, whereas phreatomagmatic eruptions do have magma involved. But this is becoming a bit of a gray area. But some of the questions that we're asking is, do these deep magma injections disrupt hydrothermal systems? Is that the underlying cause of these eruptions? Or does the failure of hydrothermal seals release magmatic gases, and can this process disrupt stagnant shallow magmas to remobilize magmatic activity? And how important is the role of external water as a coolant? And is the fuel interacting with this water, is it actually direct interaction of magma with water, or is it actually superheated magmatic gas that's being injected into these hydrothermal systems and generating boiling? So turning now to a couple of examples outside of Costa Rica, the 2014 Ontake eruption has been well studied, and this recent paper by Miyagi et al. Suggests that there was 7 years between magma injection and this eventual eruption in 2014. Just to point out, after carefully looking at the ashes, they found that there is a small component of juvenile material in this, but they stick with the term phreatic. The other interesting conclusion that they came with regarding these ashes is that they're sampling from a zoned hydrothermal system. So again, what we're seeing at the surface of these crater lakes are just a very superficial expression of a very deep and complex hydrothermal system, which I think is something that's important for us to recognize. Another example from New Zealand, this is the 2007 Ruapehu eruption. And in this paper by Christensen et al., 2010, they discussed these cyclical processes and factors leading to phreatic eruption events. And again, they found 5% of juvenile material in the deposits, but maintain that this is accidental magma and that the dominant process was phreatic due to hydrothermal sealing. Another New Zealand example is the 2012 Mount Tongariro eruption. And the ashes were studied by Pardo et al. 2014, again highlighting this problem that we have in distinguishing phreatic from phreatomagmatic ash. What we see here is something similar to what we've seen at Poas and Turrialba now, is that these kinds of eruptions are associated with a big range in juvenile or magma compositions that are involved. So the question again is what is the role of this magma, and if it's actively participating or if it's entrained in these phreatic eruptions. So 2019, we published this paper on Poas, again looking at these gas compositions. And some of the processes that we think were important in this eruptive sequence is that in 2014, when we saw these very small phreatic eruptions, we thought that these were mostly driven by gas, injections of magmatic gas. And these small eruptions serve to keep the conduit open. So for some reason in 2015, hydrothermal sealing took over as the dominant process, resulting in a big change in gas compositions. And then right prior to the main eruption in 2017, we saw these big changes in the gases, which we attributed to initial failing of the hydrothermal seal. So the 2017 eruption sequence started off with a phreatic explosion, which we interpreted to have released the pressure in the shallow magmatic system, remobilizing it and leading to phreatomagmatic and magmatic eruptions, which followed. And the change between phreatomagmatic and magmatic fragmentation processes can change very quickly during one eruption. What we saw there was a cinder cone forming around a small vent. And when that cinder cone was breached by water, then we saw more phreatomagmatic type of activity, which was then sealed off again from the water, and then goes back to more strombolian-like activity. So these can be very complex eruptions. In 2018, John Stix and I wrote this paper titled Understanding and Forecasting Phreatic Eruptions Driven by Magmatic Degassing. Again, linking some of these processes directly to magmatic processes. And we think that there are at least two types of phreatic eruptions. One is where this sealing process is determining the eruptive behavior, and type 2 phreatic eruptions, which typically occur through crater lakes, where fuel, water, coolant type interactions are more dominant. In terms of this, these overpressured hydrothermal systems or hydrothermal magmatic systems, one way to describe them could be phreatovolcanian, just because of what the eruptions look like from macroscopic observations. And I think that Diana's recent paper on Tolika is a great example of how these eruptions can work. Whereas these phreatic eruptions that occur through crater lakes, they look macroscopically like Surtsian type eruptions. So this could be an alternative way to describe some of these eruptions without getting into detailed discussions of what the dominant mechanism is, requiring detailed microscopic analyses, for example. That's based on actually this figure from Cass-and-Wright 1987, which used this term phreatoclinian. So potentially we could put phreato in front of any eruption style that we suspect is dominated by the hydrothermal system. The main point being, I think that I think it would be more useful if we could classify eruptions based on macroscopic observations of eruptions and initial field observations of eruptive deposits, rather than going back and looking at these eruptions in great detail and potentially having to change how we classify them. The other, I think, important thing to note about these systems, again, is that the hydrothermal systems are very complex and zoned. So in the economic geology literature, there's a lot of work that's been done looking at porphyry copper systems and at advanced argillic alteration, for example, and how all of these alteration zones are related to fluid compositions and physiochemical properties of these systems. So potentially by looking at these fossil systems, and as was done by Miyagi et al., using eruptive ashes to reconstruct where some of these samples are coming from, can potentially lead to a much better understanding of how these systems work. But a couple of questions that I have from a volcanological point of view, especially from the gases, is what are the roles of these deep brines and supercritical fluids in these deep hydrothermal systems? And how do we relate these different fluids to the seismic diversity that we see at a lot of these active magmatic hydrothermal systems? And I think just a final point that we need to consider when thinking about these eruptions is how do we distinguish if these eruptions are going to evolve to large explosive magmatic eruptions or not. And just a last Costa Rican example, if we look at the 1960s, the deposits from the 1960s Irazu eruption, we see that these deposits started out, or that the eruption started out with phreatic and phreatomagmatic activity, and then evolved to more explosive magmatic eruption that had significant impact on the country. So just to conclude, some of the main points, these smaller eruptions, I think everybody already knew this, but we're seeing just how severe this issue is of underreporting. Phreatic eruptions at these arc stratovolcanoes, I think in most cases are driven by magma. How directly or indirectly is very much open to debate and probably highly variable depending on the system. I think there are probably precursors to most of these eruptions, but in order to detect these precursors, which are often small, smaller amplitude systems, we need to modify our monitoring strategies. So in most cases, I think this would ultimately suggest putting instruments closer to the volcanoes or to the craters, but we need to balance that with safety, especially of the scientists. Again, deep magma injections can disrupt hydrothermal systems, but hydrothermal seal failure can also potentially disrupt these shallow magmatic systems. And to what extent they're disrupted, how much triggering of the magmatic system can occur is a very open question. And I think that we need to think about the terminology that we use and try to clarify it, also from a hazard mitigation standpoint, because communication between scientists and the authorities and the public is really fundamental. So on that note, I think I will leave it there.
Okay, thank you so much, Maarten, to you and your co-authors. It's remarkable to see the data sets that you've amassed and just what you can learn from this level of observation over time about this difficult problem. So I'll remind everybody, if you have questions, to please write them in the chat box, and I'm going to read them out in sequence. So we'll just keep going until we run out of questions or Maarten logs off. Our first question is from Charlotte Rowe, who asks, is anybody observing REE, which I take to mean rare earth elements, Charlotte, correct if wrong, in these materials? Referring to the analyses you have of these hydrothermally altered materials.
Well, I know that Maria Martinez is very interested in rare earth elements in the crater lakes, and this can tell us about when fresh rock or fresh magma is potentially intruded into the hydrothermal system, or potentially when new cracks open, exposing fresh rock to hydrothermal dissolution. But in the ashes and in these hydrothermally, these phreatic type ashes, and our samples, I'm not aware of anybody who's looking at that right now, but it would be certainly interesting.
Okay. The next question is from Klaus Jacob. You have these impressive pre-eruptive observed changes in gas and various seismic signals, but are they used, and how are they used to actually put out alerts and warnings? And what is the rate of successful versus failure, and the timing between warning and actual eruptions?
Well, that's a very good and difficult question to answer. I mean, so like I said, we've seen thousands of eruptions. It depends what you mean about precursor or warning. Obviously, these individual events where we're seeing tens of eruptions per day, we don't have the time resolution to be issuing warnings prior to each one of those. But leading up to these eruptive phases, I would say, these eruptive periods, that's when we can have more success in alerts. But there's a lot of things that go into actually emitting alerts. We're learning all of the time, but it's only relatively recently, for example, that we had real-time analysis of gas data. So and some of these precursors are quite short-lived, or occur only right before the eruption. So it's very difficult, involves a lot of communication, involves coming to a consensus between scientists, and all of those aspects make forecasting these eruptions officially a very difficult thing. So most of these precursors, I would say, are only recognized in hindsight, but we're getting better. We are getting better.
Yes. Okay. You're doing pretty well. So the next one is a comment from Ed Bensky, saying, I just wanted to note that the GVP eruption history is showing eruptive episodes, not individual explosions. For example, there are 15 explosions or passive ash emissions over 9 months. It will be shown as one eruptive period.
Right.
Weekly and bulletin reports will often note the individual explosions when they're clearly identified. If your review identifies ash events during gaps in the eruption history on the GVP, please let us know so that we can be consistent and update the data.
Yeah, I think
also I know a challenge for the GVP.
yeah, it's not meant as a criticism. Obviously, it's just highlighting an issue where where we need to even think about what it is that we're referring to when we talk about an eruption. Are we talking about an eruptive period, or an individual eruption? And what's the VEI that we attribute to an eruptive period? Is that a faithful description of the eruption? Obviously, by all of these are somehow a simplification of what's happening in nature.
Yes, and it's obviously important to do things consistently so that we
Right.
can try to do comparative studies, which I think has led to some of the definitions.
Yeah.
The next question is from Emily Johnson, who says, thanks, Maarten. I'm curious if you have observed a link in the time scale of the system being sealed and the size or amount of juvenile material in the following eruption, i.e. longer time scales of sealing equals larger eruptions or more juvenile material.
I don't think that we have enough data to fully answer that, but I would just point out two cases where with Ontake, which was sealed potentially for 7 years, and they saw only a small amount of juvenile material, versus POAS, where we saw the sealing process that was on the order of a couple of years, and we saw, well, eventually leading to pretty much a magmatic eruption. So I think it's going to depend a lot on the volcano. So and the individual system. I think each one of these systems behaves in a probably pretty unique way, and so maybe within one system you would see that. But I would be surprised if we saw like a global relationship between those.
And systems may even evolve from eruption to eruption. That's something we noted at Silica in terms of their strength. The next question is from Terry Plank, who asks, what do the crystals reveal about the timing of fresh magma? Have crystal clocks been applied to this problem of fresh, accidental, 7-year-old, etc. magma?
I think that's a great point. But I don't think it's been adequately investigated. And how would you do that? I mean, so in a lot of these, I think considering the diversity of the juvenile material, it'll just be a huge problem, but a very interesting one, like multiple PhD theses.
Okay, so Terry, take note. Our next question is from Carlos Miguel Valdez Gonzalez, who asks, have you observed an increase in volcanic activity correlated with the occurrence of large nearby or far earthquakes?
Another very good provocative question. We don't, so it seems like different systems behave quite differently. I think Rincon de la Vieja, after the 2012 Nicoya earthquake, showed an increase in activity and seismicity, but other nearby volcanoes that seemed like they should have erupted if this was a common process did not. So you're just bringing up another very interesting thing that a lot of people are thinking about, but that we don't have very good answers to. So yeah,
right.
again,
hopefully we may try to address through SC4D. So these are things to keep in mind.
Yeah, I think that's a huge question.
Yeah. So our next question is from Yunjin Zhang, who says, thank you, Maarten, for the great talk. Are there some evidence in terms of observations that can support hydrothermal seal failure can disrupt the magmatic system? What potential processes would you suggest for this disruption? So the top-down triggering of the magmatic via a seal failure.
Yeah, it's so I mean, I think that like the case of the 2017 POAS eruption was quite, well, I don't know about convincing, but it is an interesting thought process to try to think about what triggered the whole eruption sequence. And the further you go before the eruption, the less clear it becomes. So it just, you kind of end up in this chicken and egg sort of situation where you're never really sure exactly what the trigger was. And I think just, the more data, the more monitoring techniques, the higher frequency data that we can get, the more that we're going to learn about that.
So that suggests
and experimental approaches, I think, would be interesting.
Long-term monitoring of these systems is also quite critical.
Yep.
Okay, so there's one more official question in the box, and then if you'll tolerate one from me. So this question is from Peter Kelly, who says, thanks, Maarten, nice talk. Are there constraints on water contents of eruptive plumes that might give insight into involvement of exogenous water, or do gas data suggest equilibrium HOCS compositions? Also, what was the amount of gas erupted by POAS roughly, and what would be expected if accumulation was ongoing for 2 years?
Yeah, so there's a bunch of good points in there. I mean, so for me, I think that looking at water in these eruption columns would be fantastic. I think that can tell us a lot about where the water is coming from, but that's something that we really don't know. So for example, terms like steam-driven eruptions, to me, we're very much putting the cart in front of the horse, because we don't know if that's hydrothermal, if it's shallow meteoric, if these are deep hydrothermal brines, or if we're talking about water-rich magmatic gases, because magmatic gases are more than 90% water as well. So somehow getting a handle on that, maybe looking at delta D and delta O18 in eruptive plumes, would be just fantastic. Or if we could look at some of these hydrothermal alteration compositions in the ashes and potentially constrain where this water is coming from, or potentially looking at these juvenile clasts that show quench textures, and looking at fine scale water distribution in these clasts and isotopic compositions. Those are all things that I think would be very, very interesting. In terms of how much I did the calculation of how much gas would be accumulated in 2 years for POAS, and off the top of my head, I can't actually remember. So.
Okay, so Peter, follow up with Maarten.
Yeah.
We have a question, I think, clarification from S. Vishal Gupta, who says, thanks, Maarten, sir, very informative presentation. Do volcanic activity show changes in the GPS data observations? I saw a GPS in your presentation, and I think you did show some interesting GPS signal.
Yeah, I mean, at all of the volcanoes, we see deformation changes associated with this eruptive activity. The deformation is small compared to basaltic systems, for example, or prior to big eruptions. So these are all very fine observations. So yeah, we do see deformation associated with these, but how much of that deformation is associated with hydrothermal magmatic interaction, how much is actually directly associated with intrusion of magma. I think that those are all interesting considerations.
Yeah, that's a really good point. And perhaps maybe one last question. So one thing you mentioned was, the strength of the seal is obviously really critical for the hazard aspect of an ensuing phreatic or phreatomagmatic eruption. So the stronger the seal, the bigger the explosion. How would we proxy this? Is there in your mind some way that we could monitor the strength of that seal using our existing technology or some novel approach?
I mean, I think that the deformation shows a lot of promise on that, because if you're sealing and you're generating overpressure, then that should be reflected in the deformation, but it might be very localized right around the conduit. Okay. So that's potentially something of interest, would be to try to look at these, very, very close deformation patterns.
So potentially even using something like tilt or strain that's extremely sensitive.
Yeah.
Okay. And then I see a question from Maria Martinez Cruz. What would be the main process that might have generated such a high flux of SO2 at POAS in March, April 2017?
Yeah, so there's multiple ideas about that. I think that the magma is ultimately the source of the gas, but how much was that gas processed through the hydrothermal system or stored in the hydrothermal system and then released, and in what forms is also a big open question. And I think that, one of the good things about looking at these relatively small eruptions is that we can potentially directly measure the gases, maybe with drones or with fixed stations that can survive these eruptions. So potentially, we could use isotopes of sulfur in the gases or in the eruptive deposits to try to understand how much is coming from the magma and how much is coming from the hydrothermal system. So that's another very interesting question.
So it seems like isotopes are keys at getting to sources in terms of gas and water. So this is an important point.
From the geochemical perspective.
Yes. Okay, we'll take this final question, Maarten, if you're willing, and after this, we'll conclude the seminar. So the final question comes from Darren Tan, who says, "Hi, Maarten, thank you for the talk. At the start of the talk, you did mention thousands of explosions noted at the monitored volcanoes. How persistent are these explosions? How long do they last? And what would be the indicator of quiescence that separates these explosion time windows?"
Yeah, so
how are you characterizing or counting?
Yeah, so there's a lot of variation. So at Rincon de la Vieja, for example, it's an instantaneous explosion. The seismic and infrasound signals are often, I think, on the order of 2 minutes or something like that. And then at Turrialba, we see the other end of the spectrum, where we see these ash emissions, and again, they're ashes that are strongly dominated by hydrothermal components, and these ash emissions last for days or even weeks. So there's just a huge diversity in this class of eruptions, and at Rincon de la Vieja, for example, the amplitude of the tremor, I think, is probably one of the strongest indicators associated with a decrease in activity. At Turrialba, I mean, the number of LP events and I think the amplitude of the LP signals is also associated with that, but it seems like the changes at Turrialba are not very abrupt and can enter into some sort of very passive ash emission phase with little warning. But hopefully these, the bigger, more explosive ones are the ones that are most important for reporting and alerting and also figuring out how far they're going to go before they decay.
Okay, thank you. It's great that we have so many questions. Thank you, everybody in the audience. So at this point, I think we'll conclude the talk, and thank you again, Maarten, to you and to your colleagues for a really inspiring talk that I think shows us that there's, with observations like these and additional work, there's really a chance for progress on these problems. So thank you so much. Again, the talk will be posted to SC4D shortly if you would like to watch it or share it with your colleagues. And please keep an eye out again for our announcements on future webinars in this series. And thank you, everybody. Stay safe. And again, thank you for your participation. All right.
Yeah, thanks so much for coming and for all of the great questions.
Well, thank you, Maarten.